So I want to go through the problems that we did in class. And so what we have here is a amide. I want you guys to be able to see the generic structure of this amide right here. So we could do two R's like that, two groups coming off of the nitrogen. And so let's just highlight those pieces here. So clearly there's the carbonyl, there's the carbonyl. So this R would be that methyl group right there. We clearly see the nitrogen, there's the nitrogen. And if we expand out these R groups like this, we could say that this R is this hydrogen. Now, there's no difference if I would have said this R was the hydrogen. It doesn't matter. Either R there. So this R is, we'll call it the hydrogen, and then this R group right there would be all of that right there. So that's where all the pieces are coming from. So that would make that guy a amide. Question 2. We have a generic structure here of an aldehyde. And so we see the carbonyl right there. There's our carbonyl. The R group right there is the whole shebang. And then the hydrogen right there, where's that? That's coming off of the carbon right there. So there's our hydrogen. That's not a very well drawn hydrogen. Oops. Let's clean that up. Because we know there's a hydrogen coming off of there. So that would have to be a aldehyde. Okay, which of the Lewis structures violates the octet rule? Hopefully this was a quick problem because your eyes are getting trained to see Texas carbons. And there's our Texas carbon right there. That carbon has 5 bonds around it, so that's the no-no. So that violates the octet rule. But let's just make sure we go through some of these to make sure you can see that it doesn't violate the octet rule. So if we take a look at this carbon right there, we clearly see that there's 1, 2, 3, 4. So there's 4 bonds around it. Each one of those lines represents what? 2 electrons. So if there's 4 lines, 4 times 2, that means that there are 8 electrons around that carbon. Does not violate the octet. If we take a look at that carbon, we see 1 bond shown, and then those 3 is in a condensed formula there. So there's 4 bonds, which is 8 electrons. Okay. So if we take a look at this nitrogen, we see 3 plus 1 is 4, so that's 8 electrons. If we take a look at this nitrogen, we see 3, so that's 6 electrons, plus a lone pair, that's 8. So as you go through each one of these, you will see that. Like if we look at that carbon, we have 2 electrons, or 2 bonds right there, so that's 4 electrons. And then 2 other bonds right there, so there's another 4 electrons, so 8, and so forth. So you can also have carbocations that look like this, and that carbon in the center, right there, how many electrons are around it? There's a bond there, there, and there. So that's only 6 electrons. So you can have less than 8 electrons on carbon, but you can't have more. Or said another way, second row elements right there, carbons in that second row, they cannot have more than 8 electrons around their atoms. Okay, right here, what's a general structure of an alcohol? We could look at it like this. That would be a primary alcohol. or we could have a generic structure of a secondary alcohol, or we could have a generic structure of a tertiary alcohol. Now, what type of alcohol do we have here? That would be a secondary alcohol. So E would be the correct answer. And being able to identify that as a secondary alcohol is also critical for your guys' success. Make sure you remember how to do that. Okay, Lewis structure here. So the way I do this, I kind of just take it one piece at a time. And so I'm going to start right here on this carbon. And I'm just going to draw a zigzag. So where's that carbon in the zigzag? It's right there. And I can see that the carbon is connected to an oxygen atom. So I will just draw in an oxygen atom. That oxygen atom is connected to another carbon, so I'll do a zigzag down. So maybe we should number these. Atom 1, atom 2, atom 3. 1, 2, 3. Atom 3 is attached to 4, 5, 6, 7, 8, and 9. Let's number it like that. Now, as I'm numbering these things, these atoms, I'm not numbering it to name the molecule or do anything with nomenclature. It's just trying to keep track of all the pieces. Carbon 3 is bonded to carbon 4. Right there. And we can see carbon 4 is doubly bonded to a oxygen. Then that carbon is bonded to a nitrogen that has the hydrogen on it. Well, let's actually go let's put the hydrogen there, and then we'll do the zigzag up like that. So if we come back here, that would have to be atom 5. Atom 5 is bonded to a carbon 6. So we'll just do another zigzag down. Carbon... Wait. What am I... That would be carbon 6. And then carbon 7. But what do we have here? Carbon 6 and 7 are also bonded to carbon 8, shown with that triangle there. And then we see carbon 8 is connected to carbon 9. Let's CH3 like that, but we're using our zigzag, so I'll just draw a methyl group like that. So that would have to be carbon 9 right there. So now that I've drawn that zigzag right there, now I just come back and try to match it up to one of the answers. But before you do that, you could eliminate some of these right off the bat, because you know that you have a cyclopropane ring. This is a cyclobutyl, so that one's out. Okay. We also notice on the cyclopropane that there is only one methyl directly attached to the cyclopropane. So that means this guy has to be off the table because there's two of them. Then we could also see that what's coming off of the cyclopropane ring is just a methyl, one carbon. This guy has two carbons coming off of the ring. That's a sign that that's wrong. And it's also wrong because you have the nitrogen inside the three-membered ring. So that's just off the table right away. So based off of process of elimination, which I do not recommend doing until after you have actually drawn the problem or the answer by yourself, then you can go back. And so it's between 2 and 3. So what's the difference between molecule 2 and 3? Simply the location of this oxygen atom. So if we come back, here we see that the oxygen atom is not directly attached to the carbonyl. In molecule 3, we see that the oxygen is directly attached to the carbonyl carbon. And that is not what we see in molecule Z. So that would by default have to be that as the correct answer. But if you take that molecule 2 and compare it to the structure that I've drawn here, you will see that they are identical. Now, are they oriented in a different way? Yes, of course they are, because molecules can rotate in 3 dimensions. So the way the answer is given isn't necessarily the way I drew it here, but you can see if you rotate this molecule 180 degrees that you would in fact get the same thing. So those 2 things are identical. Okay, what we have here is a generic structure of a ether. So we have our oxygen clearly right there, an R group, methyl, R group, everything else. So that would be our ether. Question 7, generic structure of a carboxylic acid. OH, OH, carbonyl, carbonyl, R group, R group. Carboxylic acid would be D. This is a amine. So generic structures of amines look like this. So this one would be a primary amine. Secondary amine. So what type of amine do we have in the question? That would have to be a primary amine. Question or answer A. What that would be a tertiary amine, and then a quaternary amine would look something like that. And those are generic structures, so we could put R groups if we wanted to. Okay, that should be an R, that should be an R group. For the tertiary though, yep, that would be it. Okay. Question 9. First off, let's just annotate what we have here. We have a benzene. We could also say that we have an alcohol. We have an alcohol there. What do you think that species is with that nitrogen right there? That would be an amine. What type of an amine? Let's pay close attention. That nitrogen right there is attached to a carbon, carbon, and a carbon. So that would be a tertiary amine. This guy right here would be a ketone. This guy there would be an ether. Now when we look at the answer choices here, if we look at answer choice A, do we have an amine? Yes. Do we have a phenol? Well, I may not know what that is. So do we have an aldehyde? No, we do not. Do we have an ether? Okay. So I don't know what a phenol is, but I definitely know I don't have an aldehyde. So that guy's out. So amine, check. Phenol, I don't know what it is. Do I have an amide? No, I do not. Do I have an alcohol? Yes. But since I don't have an amide, that's off the table. Do we have an amine? Yes. Don't know what a phenol is. Do I have a ketone? Yes. Do I have an alcohol? Yes. So that one's a potential. Do we have an ether? Yes. Ketone? Yes. Amide? No. Off the table. And then ketone? Yes, don't like that one. Trying to change the color here. Let's do some blue. Ketone, yes. Phenol, I don't know what it is. Alcohol, yes. Do we have an ester? No, we do not. So by process of elimination here, because sometimes you may see things that you don't know, and so you are going to have to use process of elimination, and so you would have to say answer choice C makes the most logical sense. But from this exercise, you have now learned something. What is a phenol? A phenol is simply a benzene ring that has an alcohol attached to it. So that whole thing right there is called phenol. Right? Hopefully that makes sense. Okay, question 10 here. So what I like to do is I just count how many carbons there are before you get to the first parenthesis. And I see that there's 3 carbons, so I just quickly draw 3 carbons. 1, 2, 3. And then this carbon right here is directly attached to that carbon. So I'm going to draw another carbon. So if I number these things, 1, 2, 3, 4. 1, 2, 3, 4. I can see from the diagram here that carbon 3 has 2 methyl groups attached to it. So I will draw in my 2 methyl groups. Carbon 4 has 2 ethyl groups attached to it. So what I have to do is draw 2 carbons. 1, 2, there's my first ethyl group. And then 1, 2, there's my next methyl group. I kept saying methyl, my apologies. That's 2 carbons, so that's ethyl. So there's an ethyl, there's an ethyl. This hydrogen that you see right there is in fact there, but we don't need to show it. So that's what we have. And so that is our structure. Now, recall from class that these bonds right here, they're sigma bonds or single bonds. And there's going to be free rotation around a single bond. So I could have very well have drawn this molecule to look like this. So what did I do? I just took this guy and just put it over there. And you can do that because there's free bond rotation around single bonds. And so what's the relationship between these 2 molecules right here? They're identical. They're the exact same thing. They're just different conformers of one another. Okay? And conformers are molecules that look different on a piece of paper, but they only look different because of the free bond rotation around a single bond. But they are exactly the same. And so when I take a look here at that guy, that looks exactly like that guy right there. Okay, so that would have to be answer choice A. Let's see, question 11. Do the same thing. There's 1, 2, 3, 4 carbons in a row without any parentheses. So 2, 3, 4. It's always good to get, when you're learning this, to number things. Okay. So when you look at carbon 4, what's attached to it? It says that there's a hydrogen attached. And so, is this oxygen attached to a hydrogen? So, do you just go like this? No, you don't, because you know basic principles. Does hydrogen form 2 bonds? No, it doesn't. So that's not a good way to do it. So what's the next logical thing? The oxygen atom is going to be attached to carbon 4. So I'll draw in an oxygen. Is that a good structure? Well, think about it. This carbon right here has only one hydrogen shown there. But look at the carbon. It only has 3 bonds to it. So is it, what's the formal charge? Well, the way I've drawn it, the formal charge would be a plus 1. But there's no formal charges shown in that condensed formula. The oxygen is neutral, the carbon is neutral. If you take a look at the oxygen the way I've drawn it, you'll see that there's an oxygen with only a single bond. That can happen, but if that's the case, then that would have to be a negative charge. And there are no charges. And so you would have to do a double bonded to that carbon. And so what do we have? We have a aldehyde. And that's a telltale sign of an aldehyde when it's written like that, CHO. And so the molecule that I've drawn matches this guy right there. Why does D is an aldehyde? Why is that one wrong? It's simply just a carbon count. There's 1, 2, 3, 4, 5. And there's only 4 carbons in this guy. So that's why that one's out. But looking at this, once you guys get really good at drawing your skeletal structures, look at how fast you can do, let's say, process of elimination. You would be like, okay, this has 4 total carbons. So that has 4 carbons. That has 5, so that's out. This one, 1, 2, 3, 4. That has 4, so that's in. This one, D, has 5, so that one's out. So look at that. Just knowing how many flipping carbons there are, you get this problem down to a 50-50. And then you see that right there. That is definitely an aldehyde. And between your 2 choices, A and C, that's an alcohol. So that one's off the table. So that is your only answer choice. So like when you're in a time crunch, process of elimination is good. But if you have plenty of time, and when you're doing your homework problems, draw it out. Take it nice and slow. Make sure you can do that. And then once you guys get really good at it, obviously shortcuts are really good for being a little bit faster on exams. Okay, so let's just do this one really fast, okay, using shortcuts. There's 1, 2, 3, 4 carbons. Okay, so that one's out. 1, 2, 3, 4. You see, I'm always double checking, counting carbons. That's 5. That one's out. So now it's just between those 2. I see that. Oh, an OH, that means alcohol. Alcohol, not an aldehyde. Done. And let's see. Oh, now we have our FRQ here. Okay, identify and label an aldehyde, ketone, carboxylic acid, amide, and acid anhydride. So when you have problems like this, you have to annotate. So we could say this guy right there is a carboxylic acid. If you want to number it like 1, 1, that's fine. Or you could color code it. Doesn't matter to me. Right there, that is an aldehyde. Let's see, a amide. There's an amide. And the acid anhydride would be right there. And that's all there is to it. Okay. Are there multiple correct answers? Oh, did I not do a ketone? Ketone would be right there. There's a ketone. Okay. Identify the primary, secondary, tertiary alcohols. So where's our alcohols? There's an alcohol. There's an alcohol. And right there. Many people that aren't being careful will say that this is an alcohol. That is not an alcohol because the oxygen atom is directly attached to a carbonyl. This oxygen right there is directly attached to a carbonyl. So that would make that guy a carboxylic acid. So what would the degree of unsaturation be for this guy right here? That would have to be a primary. This one right here, the oxygen atom is attached to that carbon. How many carbons are directly attached to that orange carbon that I just labeled? Count them. 1, 2, 3. So that would be a tertiary alcohol. And the last alcohol, there's the carbon. How many carbons are directly attached to that purple one? 1, 2, making that a secondary alcohol. So let's label the amines. So this one right there would be a tertiary amine. That would be a quaternary amine. This one would be a secondary amine. And that one would be a primary amine. Do the same thing for carbons, but we don't have to do every single one. If I pointed to that carbon right there, you would call that a secondary carbon. If we looked at, let's say, on that carbon right there, that would be a primary carbon. Well, no, let's not worry about the carbons attached to heteroatoms. Don't want to. That one right there, that would be a primary carbon. Let's see, we have primary, secondary, do we have tertiary carbons? Or quaternary carbons? Well, this one right here, right there, what type of carbon is that? There's 1, 2, 3, 4 carbons directly attached to it. So that would be a quaternary carbon right there. Do we see a tertiary carbon? My eye just caught it. There it is. Because there's 1 carbon directly attached, 2 carbons, 3 carbons. So that would be a tertiary carbon. Okay, our NanoTexan. How many total lone pairs are on the eyeballs? Well, the eyeballs are clearly those guys. And those are oxygen atoms. We see that both of those oxygen atoms have 2 bonds. And if they have 2 bonds and they're neutral, there's no formal charge, then that would mean there has to be 2 lone pairs each. So that would be a total of 4 lone pairs on the eyeballs. What orbitals are used to form the bond between the eyeball and the mouth? So where's the mouth on this Texan? It's right there. Because remember from class, I was pretending that that guy right there, or that carbon right there, is a cigarette. Okay. So we're looking at which bond? The eyeball to the mouth. So we're looking at this bond right there between the oxygen and the carbon. So what orbitals are used? Well, you have to recall how to do that, which is figure out the freaking hybridization states. What's the hybridization state of that oxygen? sp3. What's the hybridization state of that carbon? sp3. So the bond is a sigma bond because you have an overlap of an oxygen atom sp3 to a carbon atom sp3. So those are the orbitals that are used. We could also say that is a sigma bond because sp3 orbitals do end-to-end overlap there. And so that's all there is to it for that problem. Does the Texan have any terminal alkynes in his arms? Well, if we just look at this alkyne right there, that would be terminal because we have a hydrogen. And this one would be an internal because there's a carbon and a carbon on both sides of that triple bond. Okay. Let's see, what are the hybridization states of carbon 1, 2, and 3? Remember from class I said don't worry about the sulfur. So carbon 1, hybridization state. When we zoom in at carbon 1, shown there, how many bonds are directly attached to it? 1, 2. So that means there are 2 hydrogens coming off of there like that. So there's 4 electron groups around carbon 1, so that makes that sp3 hybridized. Carbon 2 has a hydrogen coming off of there, and it has how many bonds directly attached to carbon 2? 1, 2, 3. So that would make carbon 2 sp2 hybridized. Carbon 3, which is that carbon, is directly bonded to that carbon and that carbon right there. Or let's no, I'm doing that a little different. What do we have here is that carbon 3 has 1 electron group there and 1 electron group there. So that would make carbon 3 sp hybridized. And recall that carbons that are sp hybridized have a carbon with 1 sp orbital and another sp orbital. And you notice how that they are 180 degrees from one another. And that the orientation of the atomic orbitals help to explain the bond angle that you see here. Okay, you see from there to there, like that, it's 180 degrees. It's just a straight line. What are the formal charges of sulfur 4 and nitrogen 5? Well, the formal charge of sulfur is simply directly below oxygen, which is group 16. So sulfur has 6 valence electrons minus, let's see, 1 bond, 2 bond, 3, 4. But be very, very careful that there is this hydrogen atom right there. So we could extend that out and kind of visualize it like that. So we have 1 bond, 2 bond, 3 bond, 4, 5. So 6 minus 5 equals plus 1. So the formal charge on that sulfur would be plus 1. So this nitrogen, see how we have 2 hydrogens right there? Draw them out if it makes more sense for you to count things. So that nitrogen has 1, 2, 3, 4 electron groups. Nitrogen is in group 15, so that means 5 valence electrons. How many electron groups did we count? 1, 2, 3, 4. 4 orange circles. 5 minus 4 equals plus 1. So that right there, nitrogen 5 would have a plus 1 charge. And we could classify that as a quaternary amine.